Something happened in the last few weeks that changed what we thought we knew about the interstellar visitor passing through our solar system. New images have come in, data from telescopes we didn't expect to contribute. And what they're showing us is forcing astronomers to revise their understanding of this object in real time. This isn't just another space news roundup. Today we're covering 4 interconnected stories. The new photographs of the interstellar object known as 3I Atlas and what they actually reveal. The discovery of new cave systems on Mars that could change where we look for life. The presence of rust on the Moon, which shouldn't exist in an airless environment, and new research showing that moons orbiting distant planets might be the most likely places in the galaxy for life to emerge. These stories connect. They're all about reassessing where and how we search for answers to the biggest questions we're asking. And the Atlas comet is at the center of it, because what we're learning from this visitor is reshaping how we think about objects that come from beyond our solar system. If you find this kind of content valuable, hit the like button. It helps more people find these updates. And let's get into what's happening right now. Let's start with what 3I Atlas actually is. The designation 3I means this is the third confirmed interstellar object to pass through our solar system. The first was Oumuamua in 2017. The second was Comet 2I Borisov in 2019. And now we have Atlas, detected by the Asteroid Terrestrial Impact Last Alert System telescope in South America. Why does this matter? Because interstellar objects are extraordinarily rare. They give us a window into planetary systems around other stars. Systems we can't visit. Systems we can barely image with our most powerful telescopes. But when one of these objects passes through our neighborhood, we get a chance to study material that formed light years away under completely different conditions than anything in our solar system. That's why astronomers mobilized every available instrument to observe Atlas as it made its closest approach to the Sun in late October 2025. And that's why the data coming back now is so important. But before we get into the new images, we need to address something that's been circulating in the media again. Professor Avi Loeb is back with his theory. He's suggesting that Atlas isn't a comet at all, but potentially an alien spacecraft. He's argued this before with Oumuamua, and he's making similar claims now. Let me be clear about the scientific consensus. Astronomers who have studied Atlas extensively, who have analyzed its spectrum, its trajectory, and its behavior, have concluded that this is a comet, not a spacecraft, not a probe. A comet with characteristics that are unique because it formed around a different star, but still fundamentally a comet. Loeb's position is that we shouldn't dismiss unusual possibilities, and he's right that science should remain open to unexpected explanations. But there's a difference between remaining open and ignoring the evidence we actually have. The spectroscopic data, the outgassing patterns, the brightness fluctuations, all of it matches what we'd expect from a comet. An unusual comet, yes, but a comet nonetheless. We'll come back to why Loeb's interpretation doesn't match the observations, but first, let's talk about what instruments are actually watching Atlas and what they're capable of seeing. When Atlas was first detected, NASA and ESA immediately began coordinating observations. The Hubble Space Telescope and the James Webb Space Telescope both captured spectra and images. These are our most powerful optical and infrared instruments. They can analyze the chemical composition of the comet by breaking down the light it reflects and emits into its component wavelengths. The SPHEREX telescope also joined the observation campaign. SPHEREX was designed primarily to search for exoplanets and map the distribution of galaxies across the universe, but its infrared capabilities make it valuable for studying comets as well, particularly for detecting molecules like carbon dioxide and carbon monoxide that emit strongly in infrared wavelengths. Here's the limitation. All of these telescopes orbit Earth or sit at the Earth-Sun Lagrange points. That means they're all looking at Atlas from essentially the same direction. Same angle, same perspective. For a spherical planet, that's not a major problem. But comets are dynamic. They have jets of gas erupting from specific locations on their surface. They have tails that point away from the sun. And understanding their three-dimensional structure requires viewing them from multiple angles. That's where things got interesting in late October. As Atlas approached perihelion, its closest point to the sun, it moved into a position where Earth-based and Earth-orbiting telescopes couldn't observe it anymore. The comet was too close to the sun in our sky. The glare would overwhelm any instrument trying to look at it. For a few weeks, our most powerful telescopes were effectively blind to what was happening during the most critical phase of the comet's passage. But here's what most people don't realize. We have spacecraft scattered throughout the solar system, probes on their way to asteroids, orbiters around Mars, solar observatories positioned to monitor the sun's activity. And during those critical weeks when Earth's view was blocked, these other spacecraft had a clear line of sight. They were looking at Atlas from completely different angles, from behind the sun, from the side, and in one case from a position that put the spacecraft directly in the path of the comet's tail. This is where we got the new data, not from my flagship telescopes, but from instruments that were in the right place at the right time. Let's be honest about something. None of these spacecraft took beautiful photographs of Atlas. If you're expecting Hubble-quality images with vibrant colors and sharp details, that's not what we got. But here's what scientists care about. They don't need aesthetic images, they need data. They need to know the comet's exact position against the background stars so they can refine its trajectory. They need spectra showing which molecules are present in the coma and tail. They need ultraviolet measurements that reveal how much water vapor is sublimating from the surface. Pretty pictures are for press releases. Data is for understanding. And the data told us something crucial. The spectrum of Atlas shows that its nucleus is composed primarily of carbon dioxide ice, not water ice. That's significant because it confirms this object didn't form in our solar system. In the region where comets from the Oort cloud and Kuiper belt formed, water ice dominates. But in the outer regions of other stellar systems, or in interstellar space itself, carbon dioxide can be the primary constituent. This is chemical proof of alien origin. Not alien as in intelligent life, but alien as in formed somewhere else. In October, Atlas passed relatively close to Mars. Close in astronomical terms means millions of miles, but close enough that Mars-orbiting spacecraft had a better view of the comet than Earth did. The Mars Reconnaissance Orbiter has the highest resolution camera of any spacecraft at Mars. It's designed to image the Martian surface in incredible detail, but it can be pointed at targets in space as well. MRO captured images of Atlas as it passed by. The European Space Agency's Mars Express and Trace Gas Orbiter also contributed observations, and even the Perseverance rover on the Martian surface attempted to image the comet, though ground-based observations are limited by atmospheric distortion even on Mars. These observations refined our understanding of Atlas's trajectory. They confirmed that the orbit calculations were accurate and that the comet was behaving exactly as predicted by gravitational models. No unexpected accelerations, no course corrections, just a chunk of ice and rock following the laws of physics as it swung past the sun. The Mars observations also provided timing data. By watching Atlas from both Mars and Earth, astronomers could use parallax to measure the comet's distance more precisely than they could from a single vantage point. But the most unusual observations came from spacecraft specifically designed to watch the sun. The Solar and Heliospheric Observatory, SOHO, has been studying the sun since 1996. It sits at the L1 Lagrange point between Earth and the sun, giving it a constant, uninterrupted view of our star. One of SOHO's instruments is a coronagraph, a device that blocks out the bright disk of the sun to reveal the much fainter corona and any objects passing nearby. Coronagraphs have discovered thousands of comets over the years. Small, sun-grazing comets that plunge toward the sun and either evaporate completely or whip around and head back out into space. Atlas isn't a sun-grazer. It passed at a safe distance. But for a few days in late October, it was close enough to appear in SOHO's field of view. The images show a faint, elongated glow. The comet's nucleus is too small to resolve as anything other than a point of light. But the coma, the cloud of gas surrounding the nucleus, is clearly visible, and extending behind it, a tail. Stereo is another solar observatory, actually a pair of spacecraft that were designed to observe the sun from two different angles simultaneously. One of the Stereo spacecraft is no longer operational, but the other is still functioning, and it captured Atlas from a perspective no other instrument had. From Stereo's position, the comet appeared to one side of the sun rather than in front of it. This gave astronomers a lateral view, revealing how the tail structure changes when seen from different angles. They also obtained additional spectra, confirming the carbon dioxide signature that Webb and Hubble had detected earlier. These solar observations weren't planned as part of a comet study. The instruments were doing what they always do, monitoring the sun. But because they're positioned where they are, they happen to have the perfect vantage point for Atlas during the critical perihelion passage. And then there were the deep space probes. NASA's Psyche spacecraft is on its way to a metal-rich asteroid in the main belt. It launched in 2023 and won't reach its target until 2029. Right now, it's in cruise mode, traveling through space with most of its instruments in standby. But in late October, mission controllers woke up some of Psyche's instruments to observe Atlas. The spacecraft was in a position to see the comet from an angle that no Earth-based telescope could match. Lucy is another NASA mission, this one headed to the Trojan asteroids that share Jupiter's orbit. It's years away from its primary science phase, but like Psyche, it had the opportunity to observe an interstellar visitor passing through the solar system. These spacecraft captured spectra and positional data, not high-resolution images. Their cameras aren't designed for that kind of work at these distances, but valuable measurements that added to the growing data set. And here's where it gets interesting. One of these probes, and mission planners haven't specified which one publicly yet, flew through the outer edge of Atlas's tail. Not the bright visible tail, but the extended hydrogen envelope that surrounds all comets, a vast cloud of hydrogen atoms produced by the breakdown of water molecules. As the spacecraft passed through this region, its particle detectors measured the composition and density of the gas. This is direct sampling of interstellar material, not observed from a distance, but actually flying through it and measuring it in situ. The data from that encounter is still being analyzed, but preliminary results confirm what the spectroscopy suggested. This is material that formed in a different part of the galaxy. Atlas has passed perihelion and is now heading back out toward the outer solar system. On December 19, 2025, it will reach its closest point to Earth. But don't expect a spectacular show. The distance will be approximately 2 astronomical units. That's twice the distance from Earth to the Sun. At that range, the comet will be visible in large amateur telescopes, but it won't be a naked eye object. It won't make headlines for its appearance in the sky. But it will be observable, and that matters. From December through March 2026, astronomers will continue tracking Atlas as it moves away from the Sun. They'll watch how its brightness changes as it cools. They'll monitor whether outgassing continues or stops. They'll look for any unexpected changes in its trajectory. After March, the comet will be too faint and too far away for most instruments to study effectively. By the time it reaches Jupiter's orbit, it will have faded into obscurity. And eventually, it will leave the solar system entirely, heading back out into interstellar space on a trajectory that will take it toward other stars over the course of millions of years. This is our window. These months right now. This is when we can gather data that might not be available again for decades until another interstellar visitor happens to pass through. And while professional astronomers continue their observations, amateur astronomers are making contributions too.
Some of the most stunning images of comets don't come from billion-dollar space telescopes. They come from dedicated amateur astronomers who spend hours in the cold darkness, capturing hundreds or thousands of individual frames, and stacking and processing them to reveal details that single exposures can't show. The techniques they use are sophisticated. Multiple exposures reduce noise, image stacking brings out faint features, and careful processing can reveal structures that are invisible in raw data. For Atlas, one amateur astronomer in particular produced an image that revealed more detail than most professional observations. His name is Satoru Murata, and he's based in the United States. Using a backyard telescope and a sensitive camera, He captured a long plasma tail streaming away from the comet's nucleus. But he also captured something else, an anti-tail. Most people think of comets as having one tail pointing away from the sun. That's the dust and gas being pushed back by solar radiation and the solar wind. But sometimes comets develop an anti-tail, a spike of material that appears to point toward the sun. This isn't actually material moving toward the sun, it's an optical illusion created by our viewing angle. Large dust particles released from the comet don't get pushed back as easily as gas and small dust grains. They lag behind, forming a curved sheet. When Earth passes through the plane of that sheet, we see it edge on, and it looks like a spike pointing in the wrong direction. Murata's image also showed jets, narrow streams of gas erupting from specific points on the comet's surface. These jets are important. They tell us about the structure of the nucleus. Comets aren't smooth balls of ice. Their surfaces are covered with a dark crust, a mixture of dust and carbon-based compounds that built up over time as the outer layers sublimated away during previous passes near stars. Beneath this crust, fresh ice remains, and as sunlight heats the surface, that ice turns directly from solid to gas, a process called sublimation. The gas builds up pressure under the crust until it finds a weak point, then erupts outward in a jet. These jets can be powerful. They can alter the comet's trajectory slightly, acting like tiny rocket engines. The force is small, but over time it adds up, causing the comet to drift off the path it would follow if gravity were the only force acting on it. This is normal. Every comet does this. It's called non-gravitational acceleration, and astronomers have to account for it when calculating comet orbits. For Atlas, the jets are visible in Murata's photographs, bright spikes extending from the nucleus in specific directions. The gas streaming out creates the comet's coma and contributes to the tail. And this is where Avi Loeb's interpretation diverges from what the observations actually show.
Loeb has pointed to the jets as evidence of artificial propulsion. He suggests that what astronomers are interpreting as natural outgassing might actually be controlled thrust from a spacecraft's engines. Let's look at why that doesn't match the data. First, the jets from Atlas behave exactly like jets from every other comet we've studied. They brighten and fade as the nucleus rotates, exposing different active regions to sunlight. They correlate with the distance from the Sun, getting stronger as the comet approaches perihelion and weaker as it moves away. And the spectrum of the gas in the jets matches what we'd expect from sublimating carbon dioxide ice. If these were rocket engines, we'd expect to see different behavior. Consistent thrust in specific directions, a propellant signature that doesn't match natural cometary ices, maneuvers that serve an obvious purpose, like trajectory corrections or orbital insertions. We don't see any of that. What we see is a comet behaving like a comet. Second, Loeb has suggested that Atlas is headed toward Jupiter with the intention of deploying probes or conducting a flyby study of the planet. Then he proposes it will leave the solar system and continue to other stars. Here's the problem. Atlas's trajectory doesn't take it particularly close to Jupiter. It'll pass through the outer solar system in the general region where Jupiter orbits, but there's no indication of a targeted flyby. The orbit is hyperbolic, meaning it's not bound to the Sun. It came from interstellar space, and it's going back to interstellar space. That's not unusual. That's what interstellar objects do. If you wanted to study Jupiter, this wouldn't be the trajectory you'd choose. You'd aim for a much closer encounter to maximize the science return. And if you wanted to visit other star systems, you wouldn't spend time in this one at all unless you were studying it for a specific reason. The spacecraft hypothesis requires adding complexity that the observations don't support.
It's a more elaborate explanation for behavior that has a simpler, well-understood cause. But Loeb's ideas get attention. They generate headlines, and they raise interesting questions about how we'd recognize an artificial object if we actually encountered one. Those are valid discussions to have. The issue is when speculation gets presented as equal to evidence-based interpretation. Astronomers who have spent years studying comets, who understand the physics of outgassing and orbital dynamics, have looked at the same data and concluded this is a natural object. That doesn't mean we stop looking for unusual features. It means we don't jump to extraordinary conclusions without extraordinary evidence. Now, let's shift to the other discoveries that came out this month, starting with what we found on Mars. Mars has caves. We've known this for years. Collapsed lava tubes, wind-carved hollows, and pits formed by ancient volcanic activity. But most of what we've found are surface features, openings that lead down into darkness but don't provide access to extensive underground systems. That might have changed. New imaging from the Mars Reconnaissance Orbiter has identified several potential cave entrances that appear to lead to larger underground networks. Why does this matter? Because caves on Mars are one of the most promising places to look for evidence of past or present life. The Martian surface is harsh. It's bombarded by ultraviolet radiation because Mars has no ozone layer. It's exposed to cosmic rays and solar storms because Mars has no protective magnetic field. And it's extremely dry, with no liquid water on the surface. But underground, conditions are different. Temperature variations are smaller. Radiation is blocked by meters of rock. And if there's any subsurface water on Mars, it would be in places like this. The newly identified caves are located in regions where volcanic activity occurred relatively recently in Martian history. Relatively recently means within the last few 100 million years, which in geological terms is quite recent. Lava tubes formed during that activity could extend for kilometers underground, creating stable environments shielded from the surface conditions. Instruments on MRO have detected temperature anomalies associated with some of these openings. During the Martian day, the surface heats up dramatically. At night, it cools just as quickly. But the cave entrances show temperature patterns that suggest they're connected to larger underground spaces where the temperature stays more constant. That's consistent with caves, and it makes them interesting targets for future exploration. The challenge is access. We can't send a rover into a vertical pit without specialized equipment. Descent modules, rappelling systems, or flying drones would be needed. NASA's Ingenuity helicopter proved that powered flight works on Mars, but cave exploration would require vehicles specifically designed for that purpose. Still, the fact that we're identifying these systems now means we can start planning. And if we want to find out whether Mars ever supported life, or whether it still harbors microbial life today, caves are where we should look. But Mars isn't the only place in the solar system where our understanding is changing. Something unexpected showed up on the Moon.
The Moon has rust. That statement shouldn't make sense. Rust is iron oxide. It forms when iron reacts with oxygen in the presence of water. The Moon has iron in its rocks, but it doesn't have an atmosphere. It doesn't have liquid water on the surface. The conditions required for rust formation don't exist there. And yet, data from India's Chandrayaan-1 lunar orbiter detected spectral signatures of hematite, a form of iron oxide, in the lunar soil at high latitudes. How is this possible? Researchers have proposed a mechanism that sounds unlikely but appears to be happening. The Moon isn't completely isolated from Earth's environment. Our planet has a magnetotail, an extension of our magnetic field that stretches out on the night side of Earth, away from the Sun. For a few days each month, as the Moon orbits Earth, it passes through this magnetotail. When that happens, the solar wind is blocked. The stream of charged particles from the Sun can't reach the lunar surface during that time. And here's the key detail. The magnetotail isn't empty.
It contains oxygen ions from Earth's upper atmosphere, particles that have been stripped away and carried along by Earth's magnetic field. Those oxygen ions can reach the moon when it's inside the magnetotail, and if they interact with iron-bearing minerals in the lunar soil, and if there's even trace amounts of water molecules adsorbed onto the surface from ancient cometary impacts, the conditions for rust formation might exist for brief periods. It's a long shot. The amount of oxygen is tiny. The amount of water is even smaller. But over millions of years, even trace amounts of rust can build up. This discovery is important because it tells us that airless bodies in the solar system can have more complex chemistry than we thought. Material doesn't just sit there unchanged. Interactions between the surface and the space environment, even without an atmosphere, can create new compounds. And if that's happening on the moon, it could be happening on other airless moons throughout the solar system. Which brings us to the last discovery, and possibly the most significant one.
When we talk about the search for life beyond Earth, we usually focus on planets. Mars, because it's nearby and might have been habitable in the past. Exoplanets in the habitable zones of distant stars. Places where conditions might allow liquid water to exist on the surface. But new research suggests we've been looking in the wrong place. Or, at least, not the only place we should be looking. Moons might be better candidates for life than planets. Here's why. A planet in the habitable zone receives steady energy from its star, but that's the only energy source. For a moon orbiting a large planet, there are additional energy sources. Tidal heating is the big one. When a moon orbits a massive planet, the gravitational pull varies depending on how close the moon is at different points in its orbit. This creates friction in the moon's interior, generating heat. Jupiter's moon Io is the most extreme example. Tidal heating makes it the most volcanically active body in the solar system. But other moons experience gentler tidal heating. Europa, Enceladus, and Titan all have subsurface oceans kept liquid by this process, even though they're far from the sun, where temperatures should keep water frozen solid. Radiation is another factor. Planets like Jupiter have powerful magnetic fields that trap high-energy particles, creating intense radiation belts. Moons passing through these belts are bombarded with radiation that can drive chemical reactions in their atmospheres and on their surfaces. And orbital resonances between multiple moons can stabilize their orbits, maintaining the tidal heating over billions of years. All of this creates environments that might be more stable and more energy-rich than planets in the habitable zone. And that matters for the emergence of life. Life requires energy, not just heat, but energy that can drive chemical reactions and support metabolism. On Earth, we have sunlight and geothermal heat. On an icy moon with a subsurface ocean, you might have tidal heating, chemical energy from interactions between the ocean and the rocky core, and radiation-driven chemistry in the ice shell above. Research teams have been running simulations of moon environments around different types of planets. And what they're finding is that certain configurations, moons around gas giants in particular, can maintain stable habitable conditions for billions of years. That's longer than Earth has had complex life, which means if life can start in these environments, it would have plenty of time to evolve into something more than simple microbes. We already have missions planned to Europa and Enceladus. The Europa Clipper spacecraft launched in 2024 and will arrive at Jupiter in the 2030s. It will study Europa's ice shell and subsurface ocean, looking for signs of habitability and possibly even biosignatures. And Enceladus, Saturn's third largest moon, has an atmosphere thicker than Earth's and lakes of liquid methane on the surface. It's a completely different kind of environment, but one where prebiotic chemistry might be happening right now.
The discovery that moons are strong candidates for life changes how we prioritize missions. It changes where we point our telescopes when we're studying exoplanetary systems. And it expands the number of potentially habitable worlds in the galaxy by orders of magnitude. Because for every star with a planet in the habitable zone, there might be dozens of gas giants with multiple moons. And if those moons can support life, the universe becomes a much more interesting place.
Let's step back and look at what these four stories tell us together. We have new data on an interstellar visitor, an object from beyond our solar system that's giving us a glimpse into how planetary systems form around other stars. We're seeing that carbon dioxide-rich comets exist, that interstellar space processes these objects in ways we're only beginning to understand, and that there's still debate about how to interpret unusual features when we encounter them. We found new caves on Mars, places that could harbor evidence of past life or even present microbial activity if it exists. These aren't just scientifically interesting locations, they're practical targets for future human exploration because caves offer natural shelter from radiation and temperature extremes. We found rust on the Moon, proof that complex chemistry happens even in the harshest, most airless environments when you have the right combination of materials and energy sources. It's a reminder that we still don't fully understand how space weathering works on bodies without atmospheres. And we've learned that moons, not just planets, should be at the center of our search for life. The conditions that make life possible might be more common on tidally heated moons than on terrestrial planets in habitable zones. These discoveries aren't isolated facts, they're pieces of a larger picture. A picture of a solar system that's more dynamic, more chemically active, and more potentially habitable than we realized even a few years ago. And beyond our solar system, we're starting to understand that the galaxy is full of objects like Atlas, drifting between stars, carrying material from one system to another, possibly even seeding new worlds with the chemical building blocks of life. That's the real story. Not whether one comet is a spacecraft, but what these objects, these caves, these moons, tell us about the universe we're part of. Atlas will remain observable through March. Astronomers will continue analyzing the data that's already come in. The spectrum results will be published in peer-reviewed journals. The trajectory refinements will be incorporated into models of how interstellar objects move through the galaxy. And then Atlas will fade from view. It will continue its journey, heading back out into the darkness, moving towards other stars it will pass in the distant future. But we'll be watching for the next visitor, because now we know they're out there. 3 confirmed interstellar objects in less than a decade means there are probably hundreds passing through the solar system every year that we don't detect because they're too small or too faint or moving through regions of the sky we're not monitoring closely. Building better survey telescopes, instruments that can scan larger portions of the sky more frequently, will help us find more of these visitors. And finding more of them will help us understand what the space between stars is really like. The Mars caves will be mapped in greater detail as MRO continues its mission. Future orbiters with ground-penetrating radar will see how deep these systems extend, and eventually will send robots or humans to explore them directly. The rust on the Moon will be studied by future lunar missions. Samples will be collected and analyzed to confirm the mechanism that's creating it, and that research will feed into our understanding of how to use lunar resources when we establish permanent bases there. And the search for life on moons will intensify. Europa Clipper will arrive at Jupiter in the early 2030s. Other missions will follow, and within the next 20 years, we might have definitive answers about whether life exists elsewhere in our solar system. That's the trajectory we're on. Not just observing the universe, but actively searching for answers to the questions that matter most. Are we alone? Where did we come from? What else is out there? Atlas, the caves on Mars, the rust on the Moon, and the potential for life on distant moons, they're all part of that search. And the fact that we're learning new things every month means we're getting closer to answers. Not all of them, not yet, but closer. And that's what makes this worth following.